In this video, we're going to cover sections 9.8 and 9.9. 9.8 looks at the halogenation of alkynes, and 9.9 looks at alkylation of terminal alkynes. So halogenation of alkynes, there's not a lot that we currently understand about the mechanism, but the overall products that are observed from this reaction can be discussed. So you can see in this example, we have an internal alkyne and the presence of excess halide, so diatomic molecular chlorine or molecular bromine. Under those conditions, what we observe is the formation of a tetrahaloalkane. And so under excess conditions, we're not going to stop at the dibromoalkene stage. The pi bond remaining as the alkyne transforms into the alkene, that pi bond continue to undergo halogenation until we fully, if you will, saturate that carbon backbone with halogens. So the most common reagents, as shown, are molecular chlorine and bromine, and the solvent that's often used in the presence of these halogens is carbon tetrachloride. Now, carbon tetrachloride is no longer being sold commercially. It's hazardous to the environment, specifically the atmosphere. And so there are other chlorinated solvents like chloroform and dichloromethane that can be used in its place. Now, if we wish to obtain a dihaloalkene as opposed to a tetrahaloalkane, we have to carefully control how much of the reagent, in this case, our molecular chlorine or molecular bromine, we have to control that ratio with the alkene carefully. So if we use one equivalent of our halogen, meaning it's a 1 mole to 1 mole ratio of X2 to the alkyne, under those reaction conditions, the major product that we will observe is the formation of a dihaloalkene. Now, we can form both a cis and a trans dihaloalkene, and as shown, the major product will place those two halogens on opposite sides of the double bond, whereas the minor product of this reaction will place those two halogens on the same side of the double bond. So again, although the mechanism for this reaction is not completely understood, we do observe these particular products being formed depending upon the conditions, primarily how much of the molecular chlorine or molecular bromine is added to our reaction mixture. Now let's look at the alkylation of terminal alkynes. So previously you saw in one of the videos we discussed the acidic properties of terminal alkynes. And that was some foreshadowing to this particular part of our course, in which we take advantage of the acidity of terminal alkynes such that we can transform these terminal alkynes into useful reagents for synthesis, primarily to, as we'll see, extend the carbon skeleton or the backbone, the parent chain, if you will. So we saw previously that in order to deprotonate a alkyne to form the alkynide ion, we need to use a sufficiently strong base. And the base of choice that's often used, especially in our text, is sodium amide in liquid ammonia. And so if we use the amide ion as our basic species, it will deprotonate the alkyne and favor the formation of the alkynide ion. And then this species, in the presence of a primary alkyl halide, will act as a very efficient nucleophile to carry out an SN2 reaction. Now, when a secondary or tertiary alkyl halide is used, then we typically observe the alkynide ion acting like a base, and the E2 reaction will predominate. Nonetheless, we can use a primary alkyl halide or methyl halide as our reagent to react with this alkynide ion to generate a larger alkyne. And we'll see in the next slide that this is synthetically useful because, as mentioned, this is going to increase the parent chain, the size of the parent chain, the carbon skeleton. So the alkylation of terminal alkynes, this is useful in synthesis. And as shown in this example, we can start with ethine or acetylene. And if we react that with our sodium amide, we're going to generate the alkynide ion in the first step. And then in a second step, we'll introduce a primary halide, in this case, ethyl iodide. And so as you can see, the net result of these two steps is the formation of a larger alkyne. We've gone from a 2-carbon alkyne to now a 4-carbon alkyne. Now, because we still have a terminal alkyne, we still have a hydrogen attached to that alkynyl functional group, we can proceed to carry out this reaction a second time. And we don't necessarily have to use ethyl iodide. We could introduce whatever R group we wish, as long as we have a alkyl halide version of it. And so you can see that we will take the same reaction conditions, but now we're going to use methyl iodide as our primary alkyl halide. And the net result is that we're going to have that CH3 group added to the other side of that alkynyl functional group. So we've gone from ethine 2-carbon system to a 5-carbon system. So we have a 2-pentyne as our final product from this 2-step synthesis, where I'm treating this as a single step to give us a larger alkyne and yet an even larger alkyne after this second synthetic step. So if we need to increase the size of the parent chain, the carbon skeleton, that carbon backbone, alkylation of terminal alkynes is a synthetically useful way of doing that. So if you have any questions about halogenation of alkynes or the alkylation of terminal alkynes, send me an email and we can discuss it further. Thank you.